All right, I think my dog stopped making a bunch of noise. I had to wait for that. Good morning, everyone. Welcome back to 161. Not too many meetings left for us right now. We've got our due dates on the board to remind us, as well as let you know of a couple of new things. And you saw I took 3.3 off because that date's already passed, obviously. So we got 3.4 due on Thursday. 3.5 and 7, we will finish both of those today. Remember, 3.5, we're kind of doing it in a abridged version, a shorter version, especially in terms of what we're testing on. If we have time to come back and finish out that material at the end, we will, but really don't expect to. But we will get absolutely everything that you need to move forward with your calculus studies. So they'll be done the 27th. And then we said that test 3, which is on chapter 3 with the exclusion of 3.6 because we already tested on that, will be on April 27th through 28th. Now, I realized after I finished class that I had a 2 here. I hope I didn't say 2. I hope I didn't say February. I'm sure I said April, but I hope that it was fairly obvious that I meant April and that I meant April with the 2 there. It should have been a 4 with that. So that test is in 1 week. Just like test 1 and 2, you will have 2 days to complete it. You will get 1 attempt. You will have to show your work in Canvas, but with this one, you are allowed a calculator. Now, remember, you're not supposed to be using calculators for things like 5 plus 6 or 7 minus 9. You're supposed to be using calculators to graph polynomials to get a better idea of where their zeros are, or to confirm where an asymptote is, like we're working on in 3.5. That is what the calculators are supposed to be meant for at this level. Bigger picture ideas, not used as a crutch. So a tool, not a crutch. That's the common saying, as you've heard me say already, I know. So again, you will find a review available. It's in the same place as last time. It's in my math lab. It's interactive. It's not required, but it will help you greatly, I believe, in terms of knowing what to study. And we're going to start talking about the final exam probably next class, and if not next class, absolutely the one after that, because that's coming up in about 2 weeks. I don't want to say a date yet, but it is roughly about 2 weeks. The final exam will be cumulative. It'll cover everything, including however much we get done in chapter 4, and if we get to chapter 5, whatever we get done in chapter 5. But again, we'll talk about that more later. For now, let's go ahead and pick up where we left off with 3.5 and about the halfway point, really. And then we'll get into 3.7, and then we'll actually get a little into 4.1 as well, because 3.7 is going to go quick. It's a much simpler concept. And I'd like to remind you again, in case you see a a date on the screen that doesn't make sense, it's not for us. When I make these notes, I leave previous dates in there sometimes and don't think about it when I'm recording because I just get going. So I try and cover them up, but sometimes I miss the cover up. All right.
And let's pick up where we left off in 3.5, which was discussing the vertical asymptotes. So remember, 3.5 is all about graphing the talked about last time, so I'm not going to spend 15 minutes just staring at this and letting y'all write it down. You can get that from last class, or you can pause this one and write everything down if you haven't already. But we said that horizontal asymptotes are based on the degree of the top and the bottom, and we said that this relates to end behavior. It's like you consider the end behavior of the top, you consider the end behavior of the bottom, and then you see which one takes over the most. That's the main idea, even though I'm kind of giving you a cookie cutter approach to this. When you go into calculus, though, they teach you the non-cookie cutter version, which is what I first said, where it's you treat it like end behavior, the top versus the bottom, and see which one takes over. Hold on one second. So if the degree in the top is larger, that means that the top takes over and it's treated more like a polynomial, and polynomials shoot up or down forever, which is why there is no horizontal asymptote. If the degree in the bottom is larger, then it acts more like a 1 over x or a 1 over x squared, which is where it flattens out to 0 over time as you look at the end behavior. And we said that if the degrees are equal, then basically you're just taking the top term, sorry, the leading term in the top, dividing it by the leading term in the bottom, and you'll be left with the ratio of the leading coefficients, which is actually the horizontal asymptote. That's what the value will trend to as you go on to infinity or negative infinity. So you can already kind of see example 2 peeking its head out, but we will. So we are just the horizontal asymptotes here, if any, because some of them don't have a horizontal asymptote. All right, A. We got 7x to the third plus 9x squared divided by 2x to the fifth minus 3x to the third plus 1. So what I'm going to do to the side is I'm going to list the degrees of the top and the bottom. See, this is a rational function because it's a fraction with variables littered all over top and bottom. So the horizontal asymptote is all based off the leading term. It's based off of this term from the top and this term in the bottom. It's not necessarily the first term, it's the term that has the biggest exponent, which those have the biggest exponent top and bottom. So again, those are the only two terms I'm really needing to look at. It's this term and this term. All right, so that says that the top degree is 3 and the bottom degree is 5. The bottom is bigger than the top. B greater than T, that's bottom is bigger than the top in terms of degrees. So that means, which of these three cases are we under? Now again, I want to kind of teach you the calculus method. The calculus method says that since the bottom degree is bigger, that's the thing that takes over. Basically, as you go to infinity and negative infinity, these terms don't matter. It's just these two. And the fact that there's more in the bottom means that the bottom is what takes over. So this is like having a 1 over, if you do 3 minus 5, it's -2, or +2 in the bottom. This is what this thing tends towards as you use x values of like 1,000,000 and 1,000,000,000 and 1,000,000,000 or negative versions of those, which 1 over x squared goes to 0 because 1 divided by a really, 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 really big number is a really, really small number. So again, that's the logic. But if you like just the blatant memorization, we're under case 2. The degree in the bottom is larger, so the horizontal asymptote is y equals 0. So your horizontal asymptote is y equals 0. That is a horizontal line at a height of 0. So if you had your x and your y axes here, this drawn a little better than that. Oh, good enough. Just pretend like that's on the axis. This is the height that the function would tend towards as you go really, really big. It doesn't say anything in the middle. It just says what happens at the far left and the far right. It's end behavior. All right, so for B, we're going to do 8x to the 4th plus 2x squared minus 6 all over 3x cubed plus 2x to the fourth minus 9. It doesn't matter how many terms are top and bottom. All it matters is find the biggest term in the top based on degree, which is the 8x to the fourth. Find the biggest term in the bottom, which some people will just go with this one instantly, and that's wrong. Because this is a 3, there's a term with a bigger exponent, so you have to pay attention. So the biggest term in the bottom is actually the 2x to the fourth. There we go. So for our degrees, the top degree is the 4. The bottom degree is also 4, so they're equal. The bottom degree is equal to the top degree. So essentially what happens is, again, the calculus idea is everything that's not the leading term in the top goes away. Everything that's not the leading term in the bottom goes away as your x's get really, really, really big in absolute. And then this x to the fourth cancels this x to the fourth, so it's like it just goes towards 8 divided by 2, which is 4. Well, the memorization for a pre-calc method, if you prefer, says that if the degrees are equal, then the horizontal asymptote is y equals the ratio of the leading coefficients. Now, the answer is not just 4, it has to be y equals 4. If you just write 4 in my math lab, it's wrong. I would give you maybe like a point of partial credit on a test, but I'm not going to give you most of it because 4 versus y equals 4 are drastic distinctions between each other. So if you had a height of, say, 4, this is where your function would tend towards as you go towards really, really, really large numbers in absolute. So as you go to your negative 100, your negative 1,000,000, your negative 1,000,000,000, or positive versions of those numbers as well. Like I said, I don't want to leave this stuff here. Oh, wow, I erased way too much. Let's be a little more careful with that. What happened? There's an X missing. So again, if you're just doing the blatant memorization, it's the ratio of the leading coefficients. What you would have done is said it's y equals the 8 over the 2. Which is y equals 4, obviously. 8 divided by 2 is 4. That's how you get there from the memorization version. All right, last one. 6x to the fifth. And these could all say f of x equals. In fact, for the last one, I will write it as a, they're all functions, but I'll show the function notation. It doesn't matter whether it's there or not. Just trying to prove that point. There we go. So f of x equals 6x to the fifth plus 3x squared minus 2x plus 5 over 4x to the fourth. This exponent is a 4. I know it's on the fraction bar, so it might look like a 9. We'll clean that up. There we go. I'm having a really hard time doing a straight line today. All right. So again, we're only looking at the leading terms. X to the fifth, x to the fourth. Well, this time, the top degree is 5. The bottom degree is 4, which means the top is bigger than the bottom, or the bottom is smaller than the top. Doesn't matter which way you say that. So that means if the top is bigger, here's the calculus idea, all these other terms no longer matter. So we're only worried about these two terms. And the fact that this x to the fifth is bigger than x to the fourth, that means basically there's an x to the first left over. So this function goes like an x to the first. Again, with the 6 and the 4 there, but this is really all that's necessary because this thing, as you put really, really large numbers, x, a billion into it, it's going to stay a billion, or 3/2 times a billion, whatever. It's going to infinity or negative infinity, which means there is no asymptote. Or if you just do the blatant memorization version, if the degree in the top is larger, there is no horizontal asymptote. So I've explained these both in a pre-calc blatant memorization way, as well as a more important calculus way, which is less blatant memorization. I'll leave all that stuff. Good grief. There we go. All right, so there is no horizontal asymptote. This thing has what's known as a slant asymptote, but we're not going to study that in this course. A pre-calc course somewhere else might study it, ours just doesn't. It's something that you might get into in your pre-calc 2, once again, depending on where you take pre-calc 2. But that's the thing about math. We don't necessarily have to cover every single aspect of something moving forward, just depends on what we need moving forward. And for our calculus sequence, we don't really deal with slant asymptotes too much. And a slant asymptote is exactly as it sounds. It's just instead of having this little horizontal line, a slant asymptote means that your function ends up going towards a slanted line. So it might end up looking, let's say you had a vertical asymptote here, you might get a function that looks like this. So this is what a slant asymptote would look like. And again, that part right there is the slant asymptote. So again, not studying it in here. It's a fascinating subject. It just tells you how you're trending as you go towards infinity. And it would be in a linear method, which can tell us a lot of things. But I don't want to leave that up here because, again, not official material, but I still felt the need to describe it over 2 or 3 minutes. Okay. That is 3.5, and you're going to see the same questions listed again. If you like to learn more, when you go to the YouTube video, you can pause this, write this stuff down, and then try it out. But this is just your basic strategy for graphing rational functions. Determine any symmetry, which is optional per usual. Do your intercepts, so y-intercepts and x-intercepts. This is literally nothing new. We were doing that for polynomials. Find your vertical and asymptotes, which we just described how to do, and then additional points as needed. And that's pretty much it. It's just the one thing you have to be careful with is that those asymptotes, as you get closer and closer to the asymptote, your function is generally getting closer and closer to it. So like I said, if we have extra time that last day of class, which I highly doubt it, we'll do 1 or 2 of these, but I'm not anticipating it. I might regret doing that. Does everything look okay down here? Yes, it is. Okay. Modeling using variation. I mentioned previously that 3.7 is kind of the odd man or woman out of this chapter because it feels like a much significantly easier, that's just all sorts of modifiers we don't need. It feels like a significantly easier type of concept than the rest of them. There's no synthetic division, there's no asymptotes. It's just write an equation, plug some numbers in, find a value, rewrite the equation, plug some numbers in, find a value. This is algebra 1 idea. You just have to write the starting equation. That's the only thing that you have to come up with, and then you have to make sure you plug the numbers in the right spot. Square goes in the square peg, circle goes in the circle peg. Pay attention and you'll be okay. And there's a couple different ways we can phrase this variation. Some things will say or some textbooks, teachers, whatever, will say they are directly proportional or inversely proportional or indirectly proportional, instead of saying they vary or indirectly vary. So the word proportional has the same meaning as the word vary, which is why you kind of see these. All direct variation can be modeled as this thing, where k is a constant of proportionality, also known as a constant of variation. So again, the words proportional and variation essentially mean the same thing. Direct variation happens when as one variable increases, so does the other. So if you're selling an item at $5 per item, if you sell more items, then you're going to make more money. Selling more items, that's the number of items going up, and then you make more money because you're going to make $5 per item. So let's say originally you sold 2 items, that's $10, and later you sell 4 items, that's $20. So the number of items went up, the amount of money you made goes up. That's direct variation. And you can even kind of relate it in a simpler way. Direct variation can be simply expressed as if one item doubles, the other doubles. Direct variation, without extra modifying words in there like this little red ink over here I'll get to in a minute, means that you have a linear setup, y equals kx, where k is going to end up being a number that you find. It's not given to you. You have to find it by plugging in an x and a y, solving for k, and then just know that k is now permanently that for that problem. It is insanely simple. So all direct variation can be modeled as y equals kx, and this is when y varies directly with x. So if y varies directly with x, you write y equals kx. If I said x varies directly with y, I would instead say x equals ky. Now, admittedly, it doesn't necessarily matter that much for direct variation, but if you throw in modifiers like it varies with a cube or a square root or an absolute value, or if it's indirect variation, then that order does matter. So I want you to understand this aspect. Y varies blah, 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 blah. Y varies blah, 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 blah. That tells us the thing that should be by itself. So if I say the number of apples varies blah, 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 then I'd be calling the apples y. I could certainly use the letter a if I prefer, but that would be the thing by itself. So if I say y varies blah, 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 y goes by itself. If I say y is proportional to blah, 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 then y goes by itself. If I say your profit is proportional to blah, 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 profit is what would go by itself. All right, you can modify direct variation by saying something like y varies directly with the square of x. So when I throw in this modifier, the square of x, that's what changes. It's now an x squared. Or I could say y varies directly with the cube of x, cube root of x, excuse me, which would be y equals k times the cube root of x. I left a little space here so that you didn't think the 3 went with the k. You're never going to change the k. The k does not get powers. It does not move to the bottom. You're not going to jumble it all around. K is just going to be a number eventually. And it's known again as the constant of proportionality. Let's think back to earlier when I said, all right, every item you sell makes you $5. In that problem, the 5 would actually be the k. So I can just take the number of items I sell, multiply by 5, and that gives me my money. So if I sold 3 items, 3 times 5 is 15. If I sold 10 items, 5 times 10 is 50. But in that instance, I said, all right, every one item is $5 in terms of a sale, in terms of revenue. But I don't have to say 1 to 5. I might say if you sell 42 items, then your revenue is $7,829. And that's when you would have to figure out that value of k, because it's not a 1 to something else relationship. All right, so I already kind of very, very quickly discussed how these work. That was not what I wanted to happen. Well, I'll just hide that then. That's okay. So for these problems, you must first find the constant of proportionality by plugging in a pair of x and y values. And again, you don't have to call them x and y. You can call them whatever letters you like. A for apple, Z for zucchini, P for profit, I for item. O for orange, I wouldn't use O personally because it looks like a 0, but you certainly could. Just be extremely careful. You'll never see me do it though. So you'll make your equation first of all. That's an implied step. Then you plug in a pair of numbers that are given to you. They have to give you a pair that go together. That will enable you to find the k, the number that tells you for every one of this, it's this many of the other thing. Then they should have given you another bit of information. They'll say, all right, well, how many apples are sold if they sell this many oranges? So you plug in that one value along with the k, and that enables you to find the unknown x or y. Sometimes it's literally just plugging the numbers in and multiplying. Sometimes you have to do a tiny bit of algebra, and we'll see all of that happen. So again, there is literally nothing complicated about this. You just have to see 1 or 2, practice them yourself, and I think this is about the easiest thing you can do in Chapter 3, but that's an opinion. All right. I don't want all this stuff up here. A store notices that the apples and oranges it sells vary directly. On Monday, the store sold 10 apples and 40 oranges. On Tuesday, the store sold 50 apples. How many oranges were sold? So this is a pretty, I'm trying to save some time today by leaving all my notes just kind of pre-written already, but it's occasionally being a pain in the butt. All right, so the store notices that the apples and oranges it sells very directly. Now, first of all, this phrasing is not exactly like the phrasing I gave you, and that's intentional. In your homework problems, they're going to be the way they give you, and you don't have to really think about which one's the y and which one's the x. It's if y varies, blah, 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 that's the one that goes by itself. Here, they didn't tell us that, so it's actually up to us, but again, thankfully for direct variation, it doesn't matter. If this was an indirect variation, I would have to give you that whole order more appropriately. If anything varies with a square or a square root or a cube root or an absolute value or something like that, I have to give you a much more specific sentence. But they just say, we just say, I just say. Store notices the apples and oranges it sells varies directly. On Monday, the store sold 10 apples and 40 oranges. On Tuesday, it sold 50 apples. How many oranges were sold on Tuesday? So Monday is the completed pair. 10 apples leads to 40 oranges, or 40 oranges leads to 10 apples. It's just they're paired together like that. We're told that these things vary directly, so that's a y equals kx setup. We just have to decide, do we want to call the apples x or do we want to call the oranges x? I'm going to choose to call the apples the x and the oranges the y. That was my choice. I can flip-flop it and get the same answer at the very end because it's direct variation. And there's no square or cube root or anything like that. On Tuesday, the store sold 50 apples. How many oranges? Okay, well, let's ignore the Tuesday part for now. Tuesday hasn't happened yet. We're only on Monday. So we're going with the y equals kx, where x is the apples and y is the oranges. Now, if you want to get a sentence that goes with y equals kx, then I'm saying the apples vary directly with the number of oranges. Didn't I? Yes. Okay, just making sure I had that right. So, I'm just gonna erase this junk. Pretend like you didn't see that. That wasn't gonna work. I thought it would, and it just wasn't. So we take our y equals kx, which once again, we're calling the y the number of oranges and the x the number of apples. So we're gonna plug the 10 in for the x and the 40 in for the y. So the y becomes a 40. That's what that little arrow means, equals. The k we still don't know, we're gonna figure that out. And then x was the 10. Double arrow, so we get 40 equals 10k. You don't have to reorder those two numbers if you don't have to. I know that sounded redundant. If you don't feel like you have to, you don't have to. We'll divide both sides by 10. And what that'll give us is that k is equal to 4. Now that value is going to be true for this entire problem. This tells us for every one apple we sell 40 oranges. That's what the k does for us in a linear problem. If it's indirect variation or any of this other cube root, square root stuff, it's kind of shadier. So now what we can do is we can take this y equals kx, and we can write in the k permanently. It's now y equals 4 times x. And from here, we'll go to Tuesday. So on Tuesday, the store sold 50 apples. How many oranges did we sell? Well, 50 apples, that's the x. We said apples is x. So our y is now on Tuesday going to be 4 times 50, which is 200. So it's 200 apples. Direct variation means as one thing goes up, the other goes up. Our apples went from 10 to 50, so they went up, and our oranges went from 40 to 200. They also went up. They go up in a constant of proportionality manner, this 1 to 4 concept. But yeah, that's really all there is. Nothing too crazy. And again, if I had swapped what I called x and y, the algebra would look a little different, but you would ultimately end up at 200 apples. All right, part B. On Wednesday, the store sold 8 oranges, which clearly we're still calling the y, but let me erase it for a second. How many apples did we sell? All right, close your eyes for a second. Close your eyes, close your eyes. Why is that eraser not working? Erase, please, and thank you. Come on. Keep your eyes closed. They're closed still, right? Okay, open your eyes. I know you didn't close your eyes. On Wednesday, the store sold 8 oranges. What did we call oranges? We called them Y. See, labeling things is going to be insanely helpful. Otherwise, now you're in part B, you might actually call them X. So how many apples? Well, we're still going to use the Y equals 4X. That K is not changing. But now instead of plugging the 8 into the X, we're plugging it into the Y. So we get 8 is equal to 4 times X. And to solve that, we divide both sides by 4, basic algebra. And then what we get is 2. 2 is equal to X, X being apples, so 2 apples. The number of oranges went down, and the number of apples went down. Makes sense. All right. So direct proportionality or direct variation is pretty simple, very basic linear algebra. I can teach this to an Algebra 1 student about 2 weeks into a course. And in fact, we do. Inverse variation, the math is a step above Algebra 1, depending on what you plug in, but it's still nothing super complicated. Inverse variation instead means as one thing goes up, the other goes down. And there are a lot of things in the real world that this works with. As you press more into your accelerator in your car, as you go faster and faster, your fuel or your miles per gallon will go down. If you're kind of feathering, if you've got like say a newer sedan with a good efficient engine, you might get 40 miles to the gallon on the highway if you're feathering it. But if you really are constantly changing speed and hammering down on the accelerator, your miles per gallon, your fuel consumption efficiency is going to decrease. So that's one thing. If you increase the price of a good, the demand for that good is going to decrease because less people want something if it goes up in cost. So these relate more to inverse variation. As one thing goes up, the other goes down. So direct variation is a multiplier between the k and the x. Inverse variation is a division between the k and the x. And the k has to go on the top. It's never going to be x over k. I already kind of alluded to that earlier. The k is always the top. So if we say y varies inversely with x, that's what is going on here. Y varies inversely, I can spell, with x. That's what's happening here. Again, the thing that varies blah, 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 blah is what goes by itself. The only thing that might be more complicated here is if you have to solve for the x, you'll have to multiply both sides by that x to get it out. And that's the same thing as what we teach in earlier algebra. Chapter 1, we went over that again, clearing fractions. All right, so once again, ignore what you see on your screen for just a second. You didn't see any of that. Here we go. I'm just going to do that. So example 2, A, the amount of charge in a capacitor varies inversely with time. And this is true. If you don't know what a capacitor is, don't worry about it. It's just an electronic device that holds charges. So like when you have issues with your modem and they tell you to unplug it for 30 seconds or a minute, it's because you have to let the capacitor discharge a certain amount of energy, or it might still hold those settings. So after 2 seconds, the amount of charge in the capacitor is 10 farads. So that's just a unit of a capacitor, kind of like miles is a unit of distance. You don't need to understand what a farad is for this problem. We're just plugging in numbers and seeing what we get. What will the charge be after 30 seconds? So the amount of charge in a capacitor varies blah, 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 blah. So we've established the charge should be the y because that's the thing that varies blah, 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 blah. And then varies inversely with time, so we'll call time x. If you want to use different letters, you could use C for charge and you could use T for time. That would be perfectly fine. I'm just sticking with the classic letters. After 2 seconds, which is a time, so that's an x, the amount of charge in the capacitor is 10 farads, which is a charge in the capacitor. I know that's redundant. That's a y. what will the charge be after 30 seconds? So we're not worrying about that part yet. We got to use the paired data, the 2 and the 10. So this varies inversely, which means we're going y equals k over x, which again, we've already established that x is time and y is the charge. You don't want to do those backwards. I will admit for the last time that anything that doesn't have a square, square root, cube root, absolute value, technically it doesn't matter, but this one, it is a lot easier to get right in this order. So after 2 seconds, which is an x, the charge is 10 farads, y. So we get the y is going to be 10 equals k over the x is 2. To solve this, we multiply both sides by 2. Nothing new algebraically. 10 times 2 is 20. So 20 is equal to k. So this is the constant of proportionality for our y equals kx, which means now we can permanently write this equation between y and x as y equals 20 over x. This is not saying for every 1 second we gain 20 farads or for every 1 second we lose 20 farads. That relationship is actually much more complicated than that. So that idea of the constant being a one of this is that many of the other thing only works for direct variation, which is example 1. All right, so now let's consider the later scenario. What will the charge be after 30 seconds? They told us wait 30 seconds before we plug it back in. How much charge is in there now? So at x equals, and that's an x value, so when x equals 30, we get y equals 20 divided by 30, which is 2/3. So after 30 seconds, there's 2/3 of a farad left. So maybe the idea, and these numbers were just kind of made up on the spot, so don't take this as what you really need in your capacitor for it to reset, and different capacitors are different, have different settings, but maybe it's just you have to get under 1 farad, and that's when it's good. I don't know. Again, these numbers are slightly made up, and different routers and different devices work differently. Some capacitors are insanely good at holding a charge. Oh man, what was the example? I just had it the other day. Don't worry about it, but some are really bad at it, some are really good at it. It's just what the capacitor is designed like. Like the capacitor in your air conditioning in your home is going to be drastically different than the capacitor in your modem or the capacitor in your Xbox or whatever. Now, again, I'm not telling you need to understand capacitors in this class. All you got to do is understand using a model, plugging in numbers, and boom, there you go. All right, same stuff as right here. I really wish I had a more efficient eraser. But now we're going to go to part B. At what time will there be a 0.1 farad charge? So maybe you have a different electronic device, or maybe after 30 seconds, your modem is not completely discharged. It's electricity. It's still got those same settings. Maybe 0.1 is the magic number. Again, we're just kind of spitballing here. So, well, what is that 0.1? That's a charge, which we said the charges are going to be y values. So we're going to call that a y. And now we just take the y equals 20 over x, and we turn the y into a 0.1. So 0.1 equals 20 over x. And this is what I was alluding to earlier. The thing you need to solve for is in the bottom, so we need to get it out of the bottom. So we have to do that LCD stuff where we identify the LCD, it's the only denominator, which is x, and you multiply both sides by that. So we do x times the 0.1, x times the 20 over x. And the whole reason we do that is so there's no more fraction, the x is out of the bottom. So we get 0.1x is equal to 20. And then you're just going to divide both sides by 0.1 or multiply both sides by 10. So I'll even write out what either of those steps are. You can divide by 0.1 or multiply by 10. Because dividing by 0.1 is the classic, oh, there's a number in front of the x, divide by it to get rid of it. Or that 0.1 also counts as 1/10, so you could just clear that fraction and multiply both sides by 10. I'll do the division by 0.1. I was supposed to do that in red. And 20 divided by 0.1 is 200, or if you do 20 times 10, that is still 200. So we get x is equal to 200. X is a unit of time, which we have labeled higher above. X is time, so that means it's 200 seconds. Sorry, there we go. So it would take 200 seconds in this scenario for our capacitor to get down to 0.1 farad. And again, different capacitors have different capacitance, rates of discharge, all that stuff. This is just a made-up problem. So maybe in this made-up land, your capacitor needs to get down to 0.1 before you can replug it in, and you have to wait 200 seconds. This is like an old school capacitor, maybe. Or maybe it's new school, and it's just really good at holding charge. It can work both ways. I have some friends that are really into electronics, and I specifically remember one of them telling me that the old school Nintendos, the capacitors on them are insane. They hold for like 10 minutes before the system memory, the ROM actually completely wipes, and you can restart it. Again, just fun fact. Nothing you actually need to know. So that actually closes out everything I'm going to teach, but I will point out that there are other types of variation. Obviously, we've mentioned the things with squares and square roots. You might even see an example like that in your homework, on your review, on a test, but I want to leave that a little more open-ended to you. But you can also have joint variation, which is where you have three things interacting. So not just capacitor and time, or charge and time. Maybe you've got resistance, charge, and time all involved in each other. Or maybe you have the price of apples, the price of oranges, and the price of bananas all interacting with each other. And maybe one of these two things varies directly, and one of them varies inversely with the square. So you can see, where'd I put them? There we go. The varies directly part, so if it varies directly with x, that means the x goes in the top. If it varies inversely with something, inversely means it goes in the bottom, so the inverse word means that the y goes in the bottom, but then it's also with the square of y, which is why this is y squared. It's not x squared. I didn't say varies directly with the square of x, so no square there. But we did say it varies inversely with the square of y, so the y squared goes in the bottom. And then you would just have to plug in numbers for the x and the y to find the z. But again, the k always goes in the top. The k never goes in the bottom. There's no pluses or minuses with these. They're all multiplication and division. So I might say, all right, you got here x is your apples, y is your oranges, and then z is your bananas. And then maybe I say on Monday, we sold, let's go with 100 apples and 2 oranges. And then we want to know how many bananas did we sell. So it goes z equals, I'm sorry, I can't say question mark for the bananas. I might say we sold, oh, I forgot my number. Let's say it was also 200 bananas. So when you plug into your equation, the z is the 200, so you go 200 equals, we don't know the k, times the x is 100, over the oranges were 2, so that bottom is 2 squared. So you get 200 equals 100k over 4, which says 200 is equal to 4 goes in 125 times. And then you divide both sides by 25. Why did I hit eraser? 25 would go into 208 times. So 8 would be the constant of proportionality. That has nothing to do with for every 1 apple you sell 8 bananas or anything like that. It's just the number that goes in this equation. And then you can then finally say that z is equal to 8x over y squared. Now I could give you just the apples and oranges to find the bananas, or the apples and the bananas to find the oranges. I could give you any two to find the third. And there we go. I'm going to show this third example really quickly with all the work, but we have covered enough. So again, if I'm going too quick, you can always go to YouTube and slow it down or pause. But this is just an extra example for free. A CEO's salary varies directly with the square. So it's not just a y equals kx, because it says directly, it's y equals kx squared. And it's based on the square of the number of employees. If there are 200 employees, the CEO makes $40 million. We want to know what would happen if we halved this company. If that company only had half as many employees, what would happen to the CEO's salary? Or maybe you're considering vice versa. Maybe you started with 100 employees and you know what the CEO makes, and you want to know what happens if we double the employees, what happens to the CEO's salary. So we could be considering either order of this. So we're going y equals kx squared, because it varies directly with a square, where y is the salary, because that's the thing that varies, blah, 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 and then x is the number of employees. Well, we were told that it's $40 million for the salary, so that's the y, that's what goes on the left. And we were told it's 200 employees, so that's what goes for the x on the right. You're going to square 200. 2 squared is 4, then just double the number of zeros. So you get 40,000. So that's 40,000 times k. I just went ahead and reversed the order of those to make it more appropriate. You divide both sides by 40,000, and you'll get k equals 1,000. So you can then rewrite your original equation as y equals 1,000 times x squared. All I've done is I took this, but we now know the k is 1,000, so we wrote it this way. Now they say, what about if there are 100 employees? It says plug in 10, but it's 100. I'm missing a 0 there. So what would the CEO make if the 100 employees existed? So that's the new x. So we have 100 squared, which would be 10,000. 10,000 times another 1,000, which is 10 million. The point being here, the CEO's salary went from 40 million to 10 million. He is now making 25% of his salary because he's lost half of his employees due to the scaling of his salary versus the employee count. Is this how things work in the real world? Marginally, actually. I feel like the bigger the company, the bigger the CEO's salary gets in a non-linear fashion. If you don't believe me, look at the CEOs of like Apple and Amazon and Microsoft and Google and whatnot. But you could also say the other way, all right, if you start out with 100 employees, the CEO is making 10 million. If he manages to double his company to 200 employees, now that means he gets to make 4 times the salary because of the relationship the company has with their employees' count and the CEO's salary. If only our salary varied that way, right? Unless you work for a company that's shrinking in size. So that is variation. That is the last thing that will be tested on for test. Oh, I hit the wrong thing, didn't I? There we go. Chapter 4. I'll leave this up here and then just kind of ignore this. Exponential functions. Chapter 4 is all about exponential functions and their inverse, which is, spoiler alert, known as a logarithmic function. But let's save that for another time. Exponential functions are extremely important in this world, and they have a very basic principle. Exponential functions operate under the basic principle that it is a constant percent growth or decay. I should actually have that up there. Meaning loss over each specific time interval. When you put your money into a savings account, you are growing your money exponentially because you're gaining money every year or every month or every day, depending on how your account is set up, how your bank sets it up. Same with investing your money in stock markets and bonds and mutual funds and anything under a 401k or a 403 or a 457 or IRAs. All that stuff is essentially the same. It's just your stocks and bonds, they all change every day. It's not like you're going to have 2% every day of the year. They literally change every day based on the market, but not what I'm teaching you. So your money grows exponentially when invested. Also, when you talk about your cells replicating as you grow, from like birth to maybe a year old or some smaller time interval, that's exponential growth. And notice that I said on a small time interval. We can also model a lot of things on small time intervals one way that don't work for a longer way. Like if you want to model population growth, a lot of people will say population growth is exponential. True, if you don't look at more than like 50 to 100 years worth of time. A lot of people will say that a certain virus, you can model it based on exponential growth. And once again, true, but only for a specific amount of time, because eventually complex things involving people, those models tend to fall apart. You can actually model population with a linear model if you only look at like 10 or 20 years, but after that amount of time, the linear model starts to fall apart and you have to go exponential. Then after an amount of time, that model falls apart and you have to go to something called logistical, which accounts for the fact that at some point we're going to run out of room and food, so there's a maximum population to our planet in theory. So the closer we get to that, we slow down, but again, it has nothing to do with exponential growth. All right, so exponential functions, constant percent growth, and they are of the basic f. What happened there? This is the basic function. I can't do that way. They are of the basic form of f, of a function f of x. F of x equals b raised to an x. Now, when you look at this, you're probably thinking, Mr. Beckner, we've seen this before. We've been doing this all semester with polynomials. You had your x squared and your x cubed and your 5x to the 9th. Wrong. Think about what I just said. X squared, x cubed. Where was the x? The x was originally the base, and then the exponent was a number. We are flipping the script on that here. Now we're saying that the base is going to be the number, b is going to be a number, and that the variable will become the exponent. So exponential equations swap the idea of what we're used to being the variable and what we're used to being the number. Polynomials have a base that's a variable. Exponentials have a base that's a number. See, they flip-flop. Now, the base for an exponential, we have a couple of constraints for them. First of all, they can't be 1. If they're 1, this is the, I hit the marker. If they're 1, this is boring. This is a 1 to the x, if you let the base be 1. 1 raised to anything is 1. This is not an exponential model. This is a flat line. So that's boring and not actually exponential. That's why we say that we can't let the base be 1. Oops. Also, we need the base to be positive. I'm not saying that you can't see negative somewhere. You could see a negative written here. Or you could see a negative written here. And you might be thinking, well, Mr. Beckner, that's a negative base. No. Because negatives work differently with exponents, whether there's a parentheses around them. So what I have on the screen right here, this negative b to the x, is completely different than this. This right here, what I have on screen now, would be a negative base, because I have a negative, and it's part of the exponential piece. So you need to understand, you need to remember that negatives with exponentials are drastically different whether there's a parentheses or not. It's all about whether that negative will get repeated or not. So why do we need the base to be positive? if you let the base be negative, how do I want to say this? Your answer is going to be negative 99.9999% of the time. But it'll be positive for every even multiple of x. So it absolutely destroys the graph of it. You end up, instead of an exponential function, which I'm going to go and spoil, your exponential functions look like this traditionally. It's slow growth at first until it eventually explodes and takes off. It kind of looks like quadratic, except the left side ends up flattening out like a rational. So that's what these are going to look like. If you let the base be negative, if your base is negative, here's what's going to happen. And this is really weird. It's going to go to about here, and then there's a hole, and then there's just a finite point here. And then it's going to go a little further, and then there'll be a hole, and there's a finite point here. And then it'll go a little further, and then there's a hole, and then there's a finite point here. This is an extremely kooky, crazy, wacky, insane graph, and you don't want to be doing that in this course. So that's why we say that we need the base to be positive. Now again, I can do this. This is not a negative base. That just makes the whole thing negative. This right here, that graph, would not have those discontinuities. It would just look like that. It wouldn't have all those little holes on every even multiple, because all the answers are negative until you hit an even exponent, and then magically the thing just turns positive because an even exponent makes a negative positive. But again, not in this form. All right. So we call b the base and x the exponent. Polynomial versus exponential form, very important to understand. Now what we want to do is we're going to figure out what the graph of a basic exponential would look like by doing something we'll never do again, which is by using several points. And close your eyes for a second. Keep them closed. I'll tell you when to open them. Keep them closed. I know they're not closed, so it just entertain me. Da, 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 da. I knew that was going to happen. Okay. A little better. Perfect. Okay. So this is my choice of x values, and you go, oh, wow, Mr. Beckner, you went back to simple x values. When you did that rational 1 over x, you were using wackadoo x is equal to 10, 100, 1,000, and 1/10, 1/100th, 1/1000th, and 1, things like that. Well, we're just going to go from -3 to 3. This will give us the whole picture. So we're just going to plug these in, and I'll do that in red. So f of -3. I won't necessarily show all of these. That would be 2 to the -3rd. Uh-oh, negative exponents. What do? Reminder from day 1, day 2 of class. That's review material. Go back to the review material if you don't remember, but negative exponents mean flip the base. So that's 1 over 2 to the 3rd. And you change the sign of the exponent. 2 cubed is 8. So that's 1/8. So when you plug in -3, you get an 1/8. How about when you plug in -2? That's 2 to the -2, which is 1 over 2 squared, which is 1/4. Again, negative exponent, swap the base, make it positive. About -1. That's 2 to the -1, which is 1 over 2 to the +1, which is a half. If you didn't write the +1 there and just finished, that would be fine as well. So that's a half. If you plug in 0, you get 2 to the 0, which anything to the 0, reminder, is not equal to 0, it's equal to 1. And here's what's very interesting. It doesn't go through the origin. That is actually the stable point that we tend to plot and shift around if we need to shift things. It's not 0, 0, and then move it left, right, up, or down. It's 0, 1. F of 1 is 2 to the 1st, which is just 2. It's a little simpler now. F of 2 is 2 squared, which is 4. And then f of 3 is 2 cubed, which is 8. Before we make the graph, I want you to observe the pattern. look at the x's. I'm going up in increments of 1. So I've got a pattern here. Every time I go from -3 to -2 to -1 to 0, I'm going up 1. I'm going up 1. I'm going up 1. I'm going up 1 every time. These y values are not going up 1. They're not going up 2. They're not going up 5. They're not going up 17 or anything like that. They're doing something a little different, and it's a lot easier to tell with these three values. Sorry about that. 1 versus 2 versus 4 versus 8. Do you think you could predict what the next one would be? It's not 0. I'm just saying, do you think you could predict it? 1, 2, 4, 8. I would predict 16 because it seems like each of these is doubling. So it seems like you times 2 to go from 1 to 2. It seems like you're timesing by 2. It seems like you're timesing by 2. In fact, it works with the fractions as well. An eighth times 2 is a fourth. A fourth times 2 is a half. Half times 2 is 1. That's the pattern with exponentials. Every time you go up 1 in the x's, the y values are doubling or tripling or quadrupling or halving or quartering or 1/10ing. And you know how you can figure out what this number is? This times 2, this times 2, this times 2. Guess what? It's right there. It's the base. That tells us that we double each time. Remember what I said earlier? Constant percent growth each interval. Constant percent growth is like we're doubling each time. But we don't have to double each time. It can go up 10%, it can go up 3%, it can go up 1%, which is usually what our money's doing in a savings account, going up 1 or 2% per year. All right, so how about those points? How about those points? -3, 1/8, that's left 3 and then up just barely. -2, 1/4 is left 2 and up, I'm going to say just barely, but a little more than last time. -1, 1/2 is left 1 up a half, which still feels like just barely, but a little more. 0, 1 is left to right nothing and up 1. 1, 2 is right 1 up 2. 2, 4 is right 2 up 4. 3, 8 is right 3 up 8. I'm going to draw the right half first, as best as I can. Sorry if it looks like there's a little bend there, it shouldn't. There we go. And then what happens is we just extend the pattern. It keeps doing this. It keeps growing quicker and quicker and quicker because the next one's going to be 16, then 32, then 64, 128, 256, 512, 1024, 2048, blah, 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 blah. These suckers grow fast eventually. How long it takes them to grow fast depends on the base. But they start out moving very, very slow. Look at this. We were at an eighth, then a quarter, then a half, and then 1. Before an eighth, we'd be at 1/16, 1/32, 1/64, 1/128. So we're never going to cross that x-axis. We just keep flattening out and getting closer and closer to 0, which means there's an asymptote. This blue dotted line represents an asymptote. Asymptotes are what things tend towards as you go left, right, up, or down forever. However, it's only one side, so you'll see some teachers draw it on both sides. That's our horizontal asymptote. But I actually only like to draw it on one side because it only asymptotes on one side. And that's a height of 0, so that horizontal asymptote is y equals 0. See, there's growth on the right and flattening out on the left. That's how exponential functions look, or vice versa. Or you see the growth on the left side and the flattening out on the right, which we call decay in that instance. So what's your takeaway from this? When your base is bigger than 1, there we go. When your base is bigger than 1, do you need to do 3, 5, 17 points? No. All you do is you plot that 0, 1. I said that's our anchor point. You grow to the right and you flatten out to the left. The flattening out on the left is a horizontal asymptote. Now again, in my math lab, you might see that dotted line extending all the way across. That's okay, you just have to understand for exponentials, they only flatten out on one side. So if the left flattens out, the right side is exploding. If the left side's exploding, the right side's flattening out. Rational equations flatten out on both sides if they have a horizontal asymptote. So you just draw something that looks like a quadratic on the left. You draw something that has that asymptotic feature of rationals on the left side, growth on the right, asymptotic on the left, boom, that's it. Kind of feels like you're drawing a weird C, which also kind of looks like part of a rational. Well, it turns out, I'm going to go ahead and spoil this. No, I'm not. You can see it, but what if we did, I thought I had that example written. Why don't I? But there was a big chunk of empty space. I feel like it got erased on accident. So example 1a, and I even have it called a. So b, f of x is equal to 1/2 raised to the x. So we said earlier your base has to be bigger than 1. I'm sorry, bigger than 0, but not 1. I said that incorrectly. Your base has to be bigger than 0, but not 1. This is under that case. Now it's just between 0 and 1. With spoilers, it makes a big difference if your base is bigger than 1 or if it's less than 1. By less than 1, I mean between 0 and 1. So when you go to do your table of values, I'm going to use the exact same -3, -2, -1, 0, 1, 2, 3. I'm going to go a little quicker for the plugging in. F of -3, that's 1/2 raised to the -3, which when you have a fraction raised to an exponent, you flip the fraction and change the sign of the exponent if it's negative. So that's 2/1 raised to the +3, which is just 2 cubed, which is 8. If you plug in -2, you get 1/2 raised to the -2, which is 2/1 raised to the +2, which is 2 squared, which is 4. You plug in -1. This is the last one I'll plug in. That's 1/2 raised to the -1, which is 2/1 raised to the +1, which is just 2 to the first, which is 2. Look at this. As we go up 1 on the left, each time, we went from 8 to 4 to 2. We're halving. We're halving. So to get to the next one, we're halving it. Half of 2 is 1. Then half of 1 is a half. Half of a half is a fourth. Half of a fourth is an eighth. These numbers right here, the red numbers, are backwards from previously. That's what I was kind of describing a few minutes ago, how it's either you flatten out on the left and grow on the right or vice versa. So when you go to make this one, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Your points end up looking like this. 2, 4, 1, 2, 3, 4. -1, 2, 0, 1. You still have that 0, 1, and then it's 1, a half, 2, a fourth, 3, an eighth. Again, you see that explosion on the left side now, which we don't think about moving left in graphs. We more think about moving right, which is why we call this decay. It flattens out. It's going to go to a 16th and a 32nd, a 64th, et cetera, et cetera, et cetera. So now that horizontal asymptote is only seen on the right side. But you still have the 0, 1 point. That's what I call that anchor point. In both of these, you have the 0, 1. So that's the only point I really draw on these. And then it's just if your base is bigger than 1, you draw it the left way. If your base is between 0 and 1, you draw it this right-hand way. The fancier names for them are exponential growth when your base is bigger than 1, and exponential decay when your base is between 0 and 1. Exponential decay relates to things like radioactive dating. You can dig up fossils and figure out how old they are based on, we know that everything loses a certain amount of an isotope every 10 years or 100 years or 1,000 years. So we have these things called half-lives. And using that, we can throw it in an exponential decay model and figure out exactly how old some bones are within a year or 2 or 10 or 100, whatever they're scaling with. This will be the last thing I put on the screen, and we'll call it a day, just pointing out the domains and ranges of these for both of them. Now, this is without modifiers, without extra coefficients or extra negatives written somewhere, because those can change the game, as we'll talk about a little next time. Both of these move left and right forever, so their domains are both negative infinity to infinity. The ranges, there is no graph below, and it does not actually touch 0, which is why the range starts at 0 with an open parentheses, because it is not included and goes up forever, whether you're going up and right or up and left. So when we talk about graphing exponentials in here, this is what we're doing. We're just taking this basic picture or this basic picture and then shifting it left, right, up, or down, maybe reflecting it. In fact, what you might notice is that these two things are reflections. They are reflections of left and right. They are horizontal reflections. In other words, if you take this first one, if you treat this as a mirror, you mirror your left and right, you get this one. So that's kind of a fascinating final thing to just mention, that exponential growth and exponential decay are just horizontal reflections of each other. And if you're really good with fractions, we talked about how a fraction with a negative exponent just says to flip the base. Check this out. 1/2 to a negative exponent is the same thing as 2/1 to a positive exponent. And look at the bases here. We saw that the first graph we did was a base of 2. We saw the second one we did was a base of a half. And look at that. They're horizontal reflections of each other because there's a negative that would have been paired where the x goes. That 1 is where the x goes. And we said all horizontal changes go with the x's. They go with the inside of the core. So it's kind of fascinating that 1/2 to the negative 1 is the same as 2 to the positive 1, or 1/2 to the positive 1 is 2 to the negative 1. It works both ways. So we'll call it a day there. We have not finished 4.1. We will finish it next time pretty easily, and then we'll get into 4.2 and 4.3. So we've got to move along because we only have, I think, 3 more classes after this. So we'll start talking about the final exam next time.
Yep. So like I said, we'll start talking about the final next time. We'll continue through 4.1. We know our due dates. We know when test 3 is going to be, those 2 days in a week. Remember, test 3 will only be available in my math lab during those 2 days under the quizzes and test section. The review is at the very end of chapter 3 in the homeworks section of my math lab that is available. And remember that you are finally allowed to use a calculator for this test, but you are still responsible for showing all work. Remember, no work means I can choose to give no credit. And for things like asymptotes, I'm definitely going to be narrowing in on that work. So I can do that for individual problems too, not just the whole thing all at once. So please show your work. Please earn as much credit as you can. Besides that, have a good one, and we will see you next class.